Hello. So today in this video, we will talk about cyclic quadrilaterals and their characteristics and some properties. And after that, we will solve two examples and also practice the questions in exercise 3. So actually, we define cyclic quadrilateral as a quadrilateral of the four vertices which are on the same circumference. That means that if you are given any quadrilateral and if all the vertices of the quadrilateral are lying on a circle, then such quadrilaterals are called cyclic quadrilateral. And concyclic points are the 4 points that we can draw a circle passing through them. So that means if you're given any 4 points, of course, they are not lying on a single straight line. And if we can draw a circle that passes through all of these points, and such points are called concyclic points. As you see in this picture, actually we are given 4 different examples. In the first one, you see a square, because if you draw any square, you can draw a circle where all the vertices of a square lie on that circle. So here we have, let's say, vertex A and vertex B, vertex C, vertex D. And the second one, it is a rectangle. And let's say this one's vertex A and the B and the C and D. As you see here, all the vertices of the rectangle are lying on that circle. And the next one is, what is it? It is a trapezium, and also all the vertices are lying on the circle. And also another one is irregular quadrilateral, and all the vertices are lying on the circle. So actually these quadrilaterals are called cyclic quadrilateral. So, and also if you notice here, before we move to the next slide and before we talk about its properties, if you notice here in the first one, we know that all the angles of, what is it, interior angles of a square, they are right angles. And also it is not coincidence that the sum of the opposite angles, they form 90 degrees. And also here, right, rectangle, all the interior angles, they are 90 degrees. So the sum of the opposite angles are 90 degrees. And how about in trapezium? As you know, that since actually we know the two sides are parallel, if this angle is alpha, this angle is, what is it, 180 minus alpha. And if actually here as trapezium and these sides are equal, which means then also this angle should be alpha, right? And also this one is 180 minus alpha. Let's see here, the sum of the opposite angles, they are 180. That is not actually a coincidence. Now we will give this as a theorem and prove this. Okay, that's property number 9. It says that the opposite angles of a cyclic quadrilateral are supplementary. And we know that if the sum of two angles is 180 degrees, then they are called supplementary angles. If the sum of two angles is equal to 90 degrees, they are called complementary angles. Here it's saying that if you are given a cyclic quadrilateral, then opposite angles form supplementary angles, which means that, as you see in the picture, let's say our quadrilateral is, so from here, this one is vertex A and vertex B, vertex C, and vertex D, right? And it's saying that here, these opposite angles, angle A and angle C, their sum here, it is A, angle A plus angle B, it is equal to 180 degrees. In similar way, if I just write here angle D, let me just write capital letter here, angle D plus angle B also, it is equal to 180 degrees. Why? Because it is a cyclic quadrilateral. If the opposite angles of a quadrilateral are supplementary, then the four vertices form concyclic points. That is the converse of this theorem. Also converse is true. If it is saying that if we are given actually any quadrilateral and the sum of the opposite angles is equal to 180 degrees, which means that they form supplementary angles, then actually that quadrilateral is a cyclic quadrilateral. That means that its vertices are lying on a circle. So how do we prove that? Proof is quite simple, and we're going to use the properties that we have studied in our previous videos. Suppose that this point is the center of this circle. Okay, so suppose that this is the center of the circle, and after that, all right. So let me actually join point D with the center of the circle. So let's say just join this, and after that also join this. Okay, so from here, as you see here, angle A, right? And this one is the central angle. That is the center of the circle. Now, I don't need to write this letter because it will be messy. So if it is A, as you see here, angle A, right? And also angle, I think, anyway. So let me just write here. Angle DOB, right? They are subtended by the same arc. And the angle DOB is a central angle, or angle DAB is a circumferential angle, which means that this angle O is double A. So that is 2A. In a similar way, how about for B? Actually, angle B is subtended by the arc DAB, and also angle DOB, right? The major angle is subtended by the same arc, which means that actually this angle, it should be double B. That is 2 times B. Now 2A, 2B, they form a round angle, right? Which means that their sum 2A plus 2B, that's equal to 360 degrees. And if you divide both sides by 2, and we get the sum of these two angles. Let me just write cap here. So A plus B is equal to 180 degrees. So now we can use this as a rule now. So if you're given any cyclic quadrilateral, the sum of its opposite angles form supplementary angles. And using this property, we can get property 10. It says that exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Now, say in the picture in the diagram, it says that if this angle is theta, and the exterior angle, right, exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So, so this one is exterior angle, and this one is interior angle of that angle, but opposite of this angle we have theta, right? They are equal. Why is it so? Because we know that angle A plus angle C, they are 180 degrees, which means that here angle C is equal to 180 minus theta. So that means that this exterior angle should be, what is it, theta. Or else the converse is true. Exterior angle of a quadrilateral is equal to the interior opposite angle. And then the four vertices are concyclic points. And the next important theorem, here it says that if two angles have same side and the two angles subtending to the same side are equal, then the four vertices are concyclic points. Okay, now if you just ignore the circle here, we are talking about this angle. Let's say angle C, let's say it is alpha. It was angle D, it is alpha. All right, and these two angles, they are subtended by one side, that is AB. Simply, we are talking about two triangles, and the one angle is the same, they are equal, and both angles are subtended by the one common side, okay, AB. So then actually these points, that A, B, C, D, actually they form cyclic points, which means that actually we can draw a circle that passes through all these points. Why is it so? Now, suppose that, for example, let's say uh, that angle, actually the point D, okay, the vertex D is not lying on the circle, okay. So, and at the time, suppose since we are given a triangle ABC, right, then I can draw a circle that passes through these 3 points. Why? Because they are not collinear. They are not lying in a straight line. So suppose that if I just extend this line, for example, here, all right, like this, maybe I need to use my tool here. All right. Suppose that if I just extend this, okay, something like this, and after that, okay, let's one. Okay. Suppose that when I extend this line, then actually this angle is the same with alpha. Okay. So since it is alpha, right? And suppose that this point D, it is not on the circle. So now if I just draw this, if I'm able to draw a circle that passes through the point AB, and let's just label this one by E, right? This angle is alpha, and this angle, as I say, it is greater than whatever it is. This angle D is not equal to angle alpha, right? Which is not possible. Which means that actually our drawn circle, it must pass through the angle, I mean the point D. Okay. Let's see now one example. Given a parallelogram, it's example 6, ABCD, as you see in the picture. So ABCD is a parallelogram, which means that this side is parallel to this side, and this side DC is parallel to AB. Okay. And extend the lines BC, CD from point C to E and F respectively, such that the line BE is perpendicular to DE and line DF is perpendicular to BF. The two lines DE, BF intersect at G, as you see in the picture, so that AB, DG are concyclic points. That means that here, what is asked here? We have to show that, here we have to show that angle A plus angle B plus angle C plus angle D, that's equal to, what is it? Concyclic points, right? Of course, it is 90 degrees, but here, since A, B, C, D, where is A? Let me just circle them. Here we have A, and here we have B, and here we have, no, A, B, D, G. A, B, D, G, right? A, B, D, A, B, D, G. Okay, let me just write here A, B, D, G, and here we have D. So we have to show that these 4 points form concyclic points, which means that we can draw a circle that passes through these points. Okay, so that means that simply I have to show that either angle A plus angle G is equal to 180 degrees, or angle B, that big angle, angle B, plus angle D is equal to 180 degrees. And we are going to use property, what is it? Property 9. And it says that if you're given any quadrilateral and the sum of opposite angles is equal to 180, then actually it is a cyclic quadrilateral, right? So we have to show that angle A plus angle G, let's say, is equal to 180 degrees. So as see here, the triangle BFD and triangle DEB or triangle GEB, they are right angle triangles. And we know that actually if this angle is alpha, let's start with this, okay? This one is alpha, and let's say this angle it is beta. Okay, now from here, since actually they are two acute angles of a right angle triangle, so alpha plus beta is equal to 90 degrees. Now from here, since alpha, if you look at the triangle EGB, right, and this one is right angle, and also this angle should be, what is it? It is angle beta. So now from here, what is this angle? That is exterior angle, or what is it? Interior angles, right? They form 180 degrees. So this angle should be 180 minus beta. So we know that in a parallelogram, right, opposite angles are equal. So if angle C is 180 minus B, angle A also must be 180 minus B, right? Now, I mean beta. Now from here, if you just find angle A plus angle G, that's equal to, what is angle A? That is 180 minus beta plus angle G, that's equal to beta. And just if you simplify this, we get 180 degrees, which proves that by theorem 9, right, or property 9, actually A, B, G, D, or D, A, B, G, they form cyclic points, which means that actually that quadrilateral is a cyclic quadrilateral. Another example, in the figure, the 4 tangent lines touching the cyclic quadrilateral. So it's given that it's cyclic quadrilateral at vertices A, B, C, D. Okay, A, B, C, D, intersect at E, F, G, H. If the two diagonal lines A, B, C, D are perpendicular to each other, show that E, F, G, H are concyclic points. Okay, E, F, G, H. So here either I need to show that E, F, G, H, we are talking about uh, this point. Let me just circle them. H and G is here, and F is here, and E is here, right? So I need to show that either E plus G, angle E plus angle G is equal to 180, or I had to show that angle H plus angle F is equal to 180 degrees. So here, let me just pick one of them, doesn't matter actually. I'm going to show that angle H plus angle F, it is equal to 180 degrees. That means that they form the sum of these two angles form supplementary angles, which proves that according to by property 9, actually proves that the quadrilateral EFGH is a cyclic quadrilateral. Okay, so now again, since actually this angle is 90 degrees, okay, again, suppose that this angle is alpha. All right, and okay, which is subtended by this arc AB. Okay, and also this should be alpha because they are subtended by the arc AB. Okay, and also by this, actually, as you see here, HD is a tangent line, and suppose that if this angle is beta, okay, um, all right. So let's say if this angle is beta, okay, and this angle should be beta because the tangent line and the chord, right, and also DCA, they are subtended by the same arc. All right, and all right, how about this one? Okay, let me just restart this. We just start with alpha. Suppose that this angle, it is alpha. Okay, as you see here, it is subtended by the arc AD, and also this angle is subtended by the same arc, and also it should be alpha. Okay, so at the time, and how about this angle? Let's say this angle is beta. All right, and also this arc that's AD, and also this one is subtended by the same arc, and also it should be beta. Okay. Now from here, if it is alpha and this is beta, right? Okay, 180 minus alpha, beta, and good. All right. So actually, this alpha and beta, they must be the same. Why? Because HD and HA, they are tangent lines, so they are equal, right? So from here, I don't have to write this one. If it is alpha, then this one is alpha. This is also alpha, and also this one is alpha. Then what is this angle? Because we know that the sum of the interior angles of any triangle is 180 degrees. So that angle is 180 minus alpha, that is 180 minus 2 alpha. Okay. And also from here, if you just look at the triangle CBH, is also an isosceles triangle. So this side is equal to this side, or tangent BF is equal to BC. Okay. So now, okay, if let's say this angle is beta, right? Let's say here is subtended by the arc BC, and also this angle should be beta. Now from here, also this angle, right, it should be beta because it's isosceles triangle. And what is this here, this angle? That angle is equal to 180 minus 2 beta. Okay, so now if you look at this triangle, let me just draw here, right? DC and the intersection point, let's say it's M. But from here, what is it? From here, from this triangle, that alpha plus beta is equal to 90 degrees. So now, if you just add angle H plus angle F is equal to Angle H is 180 minus 2 alpha. Angle F is 180 minus 2 beta, which is equal to, here we have 360 minus negative 2 is a common factor. Here we have alpha plus beta, which is equal to 360 minus 2 times the sum of alpha and beta, because they are the remaining acute angles in a right angle triangle. That's equal to 90. And by simplifying this, 360 minus 180, that's equal to 180 degrees, which means that actually the points E, F, G, and H, they are cyclic. Okay. All right. Now we have 7 questions in exercise 3, and we are going to solve these questions. Okay. Question 1, in the figure, CPD and APB are straight lines, as you see in the figure. And if ACD is equal to 125 degrees, ABD is 115 degrees, and BQD is 25 degrees. Find CQB. So we need to find CQB. Okay, to find CQB, all right, so let's say this, we need to find CQB, and the CQB, let's say it is X degrees. Okay, so now since this angle is, okay, so alpha and all right. All right. So actually, let me, okay, that's X, but I need to draw a line joining the thing. Okay, let me just actually join the points Q and that point. So what we have here now, if you just join these 2 points here. Okay. So at the time, because I'm going to find, all right. So from here, this angle is 25 BQ. That is 25 degrees. As here, it is subtended by the arc BD. And also this angle, right, it is subtended by the arc BD. So which means that also this angle should be 25 degrees. And how about this angle? They are vertical opposite angles. Also, this should be 25 degrees. Now we know that the sum of the any triangle is, what is it? 180 degrees. So from here, angle A plus angle C plus 25, that's equal to 180. From here, what is angle A? Angle A is equal to 180 minus angle C. Angle ACD, that's equal to 125 degrees minus, and the what is it, at 25, 25. So that's equal to 30 degrees. So angle A is 30 degrees. Okay. So now, since it is 30 degrees, if you look at the angle CAB and also angle CQ, A, B, C, D. Okay, let me just actually call this angle P. Okay, angle CQP, they are subtended by the same arc CP, right? So this angle also, it should be 30 degrees. And how about angle PQB? PQB is subtended by the same angle with PDB. And let's say that angle is, since angle PBD is, what is it? 115 degrees, right? ABD. ABD, 125 degrees. So also this angle is 30 degrees. Also, this should be actually them, it is 30 degrees because subtended by the same arc PB. Right. So they are lying on the same circle. Now from here, then what is angle CQB? Then angle CQB is equal to CQB is equal to CQP CQP plus PQB PQB. So that's equal to 30 plus 30, that's equal to 60 degrees. So angle CQB is equal to 60 degrees. Another example. Okay. In the figure, BEC is 35 degrees and EAB is 4x and EDC is 6x. The question is, we need to find the value of x. So as you see here, what is it? This ABCD is a cyclic quadrilateral. At the same time, EDCB also cyclic quadrilateral, right? So since actually, if you look at first, let's say number one, if you look at the quadrilateral ABCE, ABCE, right? In this quadrilateral, since it is cyclic, angle A plus angle C is equal to 180 degrees. So from here, what is angle C? Angle C is 180 minus 4x. So this angle is 180 minus 4x. And how about the second one is in the quadrilateral BCDE, BCDE, right? And also it's a cyclic quadrilateral. That means that angle D plus angle B, that's equal to 180 degrees. I mean, this angle B is this angle, right? So from here, what is angle B then? Angle B is 180 minus 6x degrees. So this angle is 180 minus 6x. And number three, step three, and if you just add, if you look at the triangle BCE, right? Triangle BCE is a triangle. The sum of the interior angles, that's equal to 180 degrees, which means that here we have 180 minus 6x plus 180 minus 4x plus 35 degrees. That's equal to 180 degrees. Now we got the equation, and just by solving this, we will get the solution, I mean the value of x. So on both sides, we have 180, they have the same sign, we can just cancel them out. And minus 6x minus 4x, that's equal to minus 10x, take to the right-hand side, and here we have 10x. 180 plus 35, that's equal to 215 degrees, right? Now, if you divide both sides by 10, so dot, 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 x is equal to 21.5 degrees. Another example in the figure AB is the diameter of the center, which is centered at O, and CD is equal to DB as you see. And if ABC is 34 degrees, okay, so ABC is 34 degrees. So we are talking about this angle, 34 degrees. Find DCB. DCB, actually, it should find this angle. Let's say it is X. And since CDB is an isosceles triangle, and also this angle should be X degrees, right? And AB is a diameter, which means that this angle is 90 degrees. So that is 34. This angle is 90 minus 34, angle A, right? So angle A is equal to 90 minus 34, which is equal to 56 degrees. So angle A is 56 degrees. Right. So as see here, ABCD is a cyclic quadrilateral. So that means that this angle, right, angle D, okay, the first step, and number two is angle A plus angle D, it should be equal to 180 degrees. Angle A is 56. What is angle D? It is 180 minus 56. That's equal to 124 degrees. And now after that, in triangle BCD, angle C, angle B, angle D, that is x plus 124, it should be equal to 180 degrees. Now from here to x is equal to 56 degrees. And what is x? X is 28 degrees. So dot, 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 what is it? Angle DCB is equal to 28 8 degrees. Okay, in question 4, in the figure ABC, there is a cyclic quadrilateral where AC is an angle bisector of BAD and BCD. Prove that AC is the diameter of the circle. Okay, we have to prove that AC is the diameter, which means that we have to prove that it passes through the center, right? So now since AC is a bisector of BAD and also BAC. Suppose that this angle is alpha. Then also this angle should be alpha. And now angle BCA, let's say that angle is beta, and also this angle is beta. So which means that from here, if I show that alpha plus beta equals 90 degrees, that shows that actually angle B is 90 degrees. Okay, number one, since it is a cyclic quadrilateral, angle A plus angle C, angle A plus angle C, right? It is equal to 180 degrees. From here, what is angle A? It is 2 alpha. Angle C, it is 2 beta. That's equal to 180 degrees. So what is alpha plus beta? Alpha plus beta is 90 degrees. Now, how about in triangle ACD? In triangle ACD, right? Angle A plus angle B plus angle C, which means that here we have alpha plus angle B plus beta is equal to 180 degrees because the sum of the interior angles of any triangle is equal to 180 degrees. Now from here, what is angle B? Angle B is 180 minus alpha plus beta. And alpha plus beta is 90 degrees. So here we have 90 degrees. Now from here, angle B is equal to 90 degrees, which proves that since we know that if the circumferential angle is subtended by an arc and forms 90 degrees, then that arc is, what is it? That chord is a diameter. Okay, because here, since it is so, right, if it is 90 degrees, and this angle must be 2 times 90, that's 180 degrees, which means that AC is a diameter. Okay. Another example, another question. In the figure, AB is a diameter, as you see in the figure, and the circle is centered at O. If AB is perpendicular to CD, AB is perpendicular to CD, that means that this angle is 90 degrees. Immediately, we can actually see that it also bisects the chord CD. And AB intersects chord CP at Q, prove that QODP. So Q, where is Q? Here it is. Q and O, D, P. Actually, we need to show that they are four concyclic points. Again, either I need to show that angle Q plus angle D is equal to 180, or angle O plus angle P is equal to 180 degrees. Okay, so since O is a center, right, from here CO, right, is equal to OD. Okay, so now suppose that this angle is, let me just change the color, and suppose that this angle is alpha. Okay, so at the time also this angle should be alpha. So now if it is alpha and this angle is, let's say it is beta, and also this angle is beta, right? Now from here, what is angle O? Actually, this angle, that's equal to 180 minus beta. All right. So now, all right, as you see here, angle P, right? Angle P and angle O, they are subtended by the same arc, but angle P is a circumferential angle, and angle O is uh, a central angle, which means that by the property that we have studied in our previous videos, right? Angle P is half of angle O. I mean that angle CPD is half of angle COD. Since angle COD, right? Since angle COD is 2 beta, so angle P must be beta. Now from here, if you just add angle O plus angle P, right? Now angle O plus angle P. What is angle O? Angle O is 180 minus beta. And angle P, it is beta. So their sum is 180 degrees. So which shows that since the opposite angles, the sum of the opposite angles of a quadrilateral is equal to 180 degrees, that means that the quadrilateral is cyclic quadrilateral. Question 6. In the figure, triangle ABC is an isosceles triangle. Extend A to P and Q is a point on BC such that angle BQP is equal to angle 2 times angle QPC. Okay, angle BQP. Okay, BQP. Suppose that this angle is alpha, QPC, QPC, and let's say this angle is alpha. At the time this angle is, what is it? 2 alpha. Prove that APBQ are 4 concyclic points. Okay. A, P, B, Q. Here's Q. Okay. A, P, B, Q. Okay. BQ. A, P, B, Q. 4 constant, what is it? Concyclic points. All right. To show that LC here, just I'm going to show that actually this angle B and also this one, actually it is equal to alpha. At the time, as see here by property, what is it? Property 11, right? If two triangles have the same side and the two angles subtending to the same side are equal, then the 4 vertices are concyclic points. So we are going to use property 11. So by property 11, since actually angle, what is it? ABC is an isosceles triangle, right? And also I'm going to show that's equal to x. Okay, so suppose that here, that one is x. So if it is so, also this angle should be, it is x. Okay. Now, all right. So now from here, right, angle x plus angle alpha, it is equal to 2 alpha, right? The sum of the interior angles of any triangle is equal to the exterior angle of the third angle. So using that property of triangles, I can write here angle x plus, and just simply x is alpha. Just write here x. That's equal to the third angle is, it is this angle. Its exterior angle is 2 alpha. That is BQP. That's equal to 2 alpha. Now from here, what is x? X is equal to alpha, which shows that actually angle ABQ, that proves that angle ABQ is equal to angle APQ. Angle APQ, right? So since it is so by property 11, then the points A, P, B, Q form 4 concyclic points because they are subtended by one side AQ, which is actually, if you draw a circle that passes through the points A, P, B, Q, it will be a circle, and AQ will be a chord, an angle. That's APQ and the ABQ. They are subtended by the same arc, which means that they are equal. Or if they are equal, that means that they form 4 concyclic points. Okay, that's our last example, last problem. In the figure, AB is the diameter of the circle, which is centered at O, and AB is perpendicular to CD. AB is perpendicular to CD. Okay, that is perpendicular. And if AP, AQ are 2 chords intersect CD at R and S respectively, prove that PQSR are 4 concyclic points. PQSR. So P, it is this point. Let me just first label them. Q is here. And the S is here. Right? And R is here. Okay, so we have to show that these 4 points. Also, we can draw a circle that passes through these 4 points. Okay, so all right, let me just start from here. Since it is right angle triangle, suppose that this angle is alpha, and suppose that this angle is, what is it, beta. Okay, at the time this angle, it will be, what is it, 90 minus alpha. And how about this angle? It will be 90 minus beta. So angle A, actually simply angle A here, angle A is equal to 180 minus alpha plus beta. Okay. All right. Uh, so now from here, I can just find angle S, right? What is angle S? Angle S is 180 minus alpha, right? So see here in, what is this? Okay, 90 degrees, 180 minus beta, and angle P is subtended by the arc AQ, by AQ. Okay, 90. Alpha, beta. All right. So let me just actually, what is it? If I draw a line segment that joins the center. Okay. So at the time, actually this is a radius, and also it's a radius. If it is 90 minus beta, and also this angle will be 90 minus beta. Okay, and also they are equal, and this angle is, what is it? It is 90 minus alpha. All right. So, and how about this angle? This angle is, it's just double angle A, that is 90 plus 90, right? Angle O is, let me write here, angle O is 2 times 180 minus alpha minus beta. Okay. So if it is so, now from here, I can find this angle. Let me just write here that is X, and also this one is X, okay? Because after all, and I'm just going to prove that actually that X plus 90 minus beta is equal to just alpha. So now from the second equation, I mean the triangle POQ, if you look at the triangle POQ, right? Angle actually P and Q, that's X plus angle O, that's equal to 2 times 180 minus alpha minus beta, that's equal to 180 degrees. The sum of the interior angles of the triangle POQ. So now if you divide both sides by 2, here we have 2x. So here we have x plus 180 minus alpha minus beta. On the right hand side, we have 90 degrees. So from here, what is x? So x is equal to alpha plus beta minus 90 degrees. So now if you look actually angle P, what is angle P? Angle P is x plus 90 minus beta, right? So what is x? X is alpha plus beta minus 90, and plus here we have 90 minus beta. If you simplify this, minus 90 and 90, they cancel each other, and the beta minus beta is equal to 0, and only alpha left. So now number 4, angle S plus angle P. Angle S, actually angle S is, what is it, 180 degrees minus alpha, right? This one is 180 degrees minus alpha plus angle P. What is angle P? It is alpha. So that's equal to 180 degrees. Since by property 10, right, the sum of the opposite, I mean the sum of the opposite angles of a quadrilateral form supplementary angles, which means that PQSR form 4 consecutive points. That means it's just simply the quadrilateral PQSR is a cyclic quadrilateral.